Hello, lovely humans, Jim Foxbot here. In this episode, we are going to use our understanding of electric field lines to find the electric flux, or basically the amount of field lines that are passing through a surface. We'll use that to basically get to Gauss's law. Woo! And Gauss's law is a really handy equation when you have symmetry in electrodynamics. So the integral equation for the electric field can be a bit unwieldy. If you watched the example problem we did, you get some really painful integrals. So Gauss's law, when you have symmetry, spherical, cylindrical, or planar, can be a much easier way, more friendly way to find the electric field. Woo! Okay, so let's dig in. Okay, so to reiterate, we have this we can draw these pictures of the electric field lines, which are proportional to the strength of the electric field from a charge or charges. And then we can say, okay, well, what if I had like a piece of paper or a window or just some random surface that exists in the chalkboard universe? So my surface I drew with white lines, and it has this perpendicular infinitesimal direction vector, dA. We can set up the equation for flux. Flux is a pretty common quantity that pops up in engineering, like when you're asking how much water is flowing past a surface, et cetera, et cetera. So we're just going to define this quantity, and we can define this quantity to say, okay, well, we want to add up all of the contributions from the electric field lines in the direction of the surface, or along the surface, basically, and add them up to get the total amount of electric field lines passing through the surface. So how does this work? Well, this dot product, dA picks out, or E dot dA picks out the component of dA along the electric field lines. And to just give you a quick refresher on dot product, if you have a vector A and you dot it with a vector B, you end up, well, A dot B equals the magnitude of A times the magnitude of B times the cosine of theta. If you have B is 1 or something like that, you can also think about the dot product as being a projection of, let's see if I can do this with my arms, a projection of one vector onto the other. And so this distance here is the magnitude of A times the cosine of the angle between the two of them. Really quickly, if they're 90 degrees, cosine of 90 degrees, or pi over 2, is 0. So if they're perpendicular, they don't map to each other. So this equation allows you to go through and just add up all of the contributions of the electric field along the surface. And then because you're adding up all of them over the whole surface, you would maybe have this from like 0 to L, and then from 0 to, I don't know, W. I'd probably switch those. But basically you would do it along the whole surface, and then you would add up the contributions from all of the field lines that are passing through that surface. And remember, even though we can't draw an infinite number of field lines, the density of the field lines is proportional to the strength of the field. And so that gets us thinking and asking, okay, well, what if we had a closed surface? Wouldn't we be adding up all of the field lines from whatever charges were inside? Yeah, we would be. So this is where, this is basically the essence of Gauss's law, which basically says if we have some surface with a charge inside, it's going to have field lines that are coming out of the surface, and as we go along the surface, we're adding up all of those contributions, and we will be able to get information about the total charge inside. Okay, well, what if we have like two equal but opposite charges? Oh, that's fine, because some of the charge, or some of the field lines will not exit the surface, but there will be field lines that do. And the other question we should ask is like, well, what about an outside charge? What the heck happens here? Okay, well, let's say we have an outside charge that's radiating, that has field lines that are radiating outward. They're going to pass into the surface and then pass right back out. And since we're interested in the density of the field lines, basically this contribution will cancel, same magnitude, opposite in value, and so any charge outside will cancel as we go through the closed surface. So the closed surface is clutch. Okay, so now let's ask let's actually ask if we know this to be true, if we can prove this to be true. So let's say we have a point charge at the origin. It doesn't really matter what these are, but I am gonna get a different color. Ooh, my charge is gonna be blue, and it's gonna radiate field lines like so. Yeah. Okay. And so we can think of drawing, let's say, a representative sphere. It's a sphere, not a circle. It's very important. With a radius r. And we can ask, okay, well, number one, we know the electric field for a point charge at the origin. Whoopsies. 1 over 4 pi epsilon naught q over r squared. And so now we can plug that in to our equation for flux. So E dot dA, we're just going to straight up plug this in. Whoopsies, I forgot this is very important. Dot products only work with vectors. Okay, so we have the integral of 1 over 4 pi epsilon naught, q over r squared, r hat dot, dA in spherical coordinates for a constant radius r. It's going to give me r squared sine theta d phi, and we're sweeping over the r direction. So r hat dot r hat equals 1. If it was any other component or unit vector, we would get a 0 because they're perpendicular. And so basically these r hats go to 1, the r squareds cancel, and what we end up with is a 1 over 4 pi epsilon naught integral from theta sweeps from 0 to pi. So we're going to get a sine theta d theta, and phi sweeps from 0 to 2 pi. So from 0 to 2 pi of just a d phi. So this gives us a negative cosine theta from 0 to pi. Cosine of pi is -1, so negative and a negative is +1 minus a negative. Final minus initial is going to, cosine of 0 is 1, so this is going to give us a 2. All right, and then this one just gives us phi from 0 to 2 pi, and so this equals 2 pi. 2 times 2 pi, 4 pi. That cancels, and we just, whoopsies, I lost my q. It's like, wait a second, we're missing a very important piece. We end up with q over epsilon naught. Boom! QED, woo! So we just showed that the flux over a closed surface area equals the enclosed charge. Woo! Okay, but wait a second, we should ask, what if we have multiple charges? Does this still work? Okay. We should double check that and work through it and make sure we understand, because that is a very important question. So the electric field of multiple charges can be represented just like this, where you just have, I'll write a little total here, where you are summing up the electric field contributions from each of the charges for however n number of charges you have. And 1 over 4 pi epsilon naught, sum of qi over r squared from pi equals 1 to n. Okay, so now we just toss this in to the equation for flux, and we end up with a summation out front. Whoopsies. Well, yeah, okay. EI dot dA. And this looks like the exact same equation we just played around with. We just have this summation sign out front. So we end up with a summation sign from I equals 1 to n of qi over epsilon naught. And we can really just write qi as a capital Q enclosed to just represent that we should be totaling the charge inside. And that's honestly what this summation sign does. It's just saying, let's add up all the contributions of the individual charge, and you get Q enclosed. Woo! Okay, so that's really Gauss's law. So to write it more formally, the flux over a closed surface, that's what this circle means, equals the total charge enclosed divided by epsilon naught. Yeah! Okay, that's Gauss's law. Woo! Okay, so in the last couple of minutes, I want to get us to a point, I want to get us to the kind of like the differential form of Gauss's law, because that might be a little bit more useful. And I want to work through the process because I think it's important to understand. Okay, so what we're going to do is we are going to apply the divergence theorem, which is just a theorem in calculus that lots of smart people have worked on and figured out over the years. So I'm not doing any new physics or anything like that. It's just a mathematical theorem that we are taking advantage of, which states that the flux through a closed surface is equal to the divergence of the thing of interest, in this case the electric field, over the volume of that surface. So again, this is just a theorem of calculus. We are going to use the fact that we can write Q enclosed as the sum, or the integral, this is kind of the same thing, over the charge density of that surface. And so what we'll do is we'll write these two equal to Q enclosed over epsilon naught with this integral notation, and that's over the volume. So the divergence of E over the divergence of E summed over the total volume equals Q enclosed, which we can write like this, rho over epsilon naught d tau. And so this must be true for any volume. Doesn't matter what volume you have, because we have shown that these two equations must be equal, we can basically say, okay, well, integral aside, we know that these kind of inside pieces have to be equal because it holds true for any volume. It doesn't matter what you're integrating over, these two pieces must be equal. So then we can say, hey, look at that. The divergence of E equals the charge density over epsilon naught. Let me just make sure. Yep, okay, cool. So this is basically the differential form of Gauss's law. This is the integral form. They both are always true, but as my book likes to point out, they're not always useful, so it goes. But one of my favorite things about this process is that it enables us to get different equations to help us find the electric field for various charge configurations, which can be a really hard thing to do. So the more tricks we have to pull from, the easier our lives will be, and the more types of things we can analyze and calculate. So Gauss's law, as I mentioned earlier, really only works if you have symmetry, specifically spherical, cylindrical, or planar symmetry. And that's when these formulas are a lot easier to work with than the integral form of the electric field. Okay, cool. I'm going to leave it there for now. Let me know if you have any questions about what we covered. I will do a little bit more with Gauss's law, I think, but we are going to move on to other types of topics in electrodynamics. So feel free to request specific things, and we will go from there. Yay! All right, thanks for watching, and we'll see you next time. Bye!